Yeah.
I don't believe that, but I just take my fingers nagging whenever I miss a little spot.
No, you missed like a spot right there. I'm like, oh wait.
No one's gonna see that.
I hate to say this, but we pay someone to mow the grass.
I swear.
I hate mowing the grass. Yeah, I mean, I did it for a long time. My parents were divorced and my dad lived on this big, like,
Damn.
wasn't like an operating farm, but it was like you know, out in the country with a lot of land,
Yeah.
Oh my god.
right? And he kept the backyard like a lawn, even though it was huge, and it took like 2 or 3 hours on a riding lawnmower to mow. It's like huge. Yeah.
Oh.
All right. I think it's time to go, huh?
New software update.
Chalk. Where you at, Chalk? Do you guys know this band Of Monsters and Men? No, like really into them. Anyway, they just released a new song. They're from Iceland.
I never heard of them.
I don't know what it is with music from Iceland. It's all like good and kind of crazy. Like Bjork. You know Bjork?
No.
Sigur Rós.
No.
They're all from Iceland. Okay. So let's see. The stuff that you looked at was the notion of a normal subgroup and a factor group or a quotient group. The book uses the word factor group, but generally I use the word quotient group. I think that's more standard, is quotient group. So let's maybe recall some definitions real quick, and then we'll look at some examples. So I put the homework up. You know, we'll definitely do some problems that are near the homework problems, or even like give you guys some time to start the homework problems as we get to it. Okay. So let's recall the following definition. So if you have G, which is a group, and N, which is a subgroup, so we can just write it like that, then we say N is a normal subgroup. So it has to start off being a subgroup in order to be a normal subgroup. If, oh yeah, maybe we'll point this out too, and we write this N with this triangle. I don't know how to say that in words, but with that symbol. So we read this as N is a normal subgroup, just like we read this as N is a subgroup. And just to be really pedantic, the word, right?
No, I never heard of it.
We read this as N as a subset, right? So we're using slightly different notation for all of this stuff. So this has no structure at all. It's just a subset, a collection of the elements from G viewed as a set. This is a subgroup, so we know what a subgroup is. And then this is a normal subgroup. So we're getting more and more structure as we go down.
Is that meant to look like a triangle?
Yeah, it is. Like it's
Just making sure.
yeah, but it's closed off there. Yeah.
Gotcha.
Okay. So if now there are a bunch of different ways of writing this down. Maybe we'll write a couple of them. So one for all Gn G, Gn equals Ng. So this is the left coset of n. Well, I guess we should, yeah, the left coset of n, and this is the right coset of n. The left coset of n with representative g, this is the right coset of n with representative g. So this isn't written in a set-wise way. If you can write it in an element-wise way like this. For all n and n, there exists, maybe we'll call it an n prime in n, such that little n g equals g n prime. So like the important thing here is that, you know, the group may not be commutative or whatever, abelian. But what you can do is you can slide G past an element from N, and you pick up another element from N. So you still stay inside of the subgroup if you slide past G. And that's for any G. Okay, so that's maybe one definition. And then the other definition, which is standard, is like this. So for all Gn G, Gn G inverse is equal to n. And I'm going to go ahead and quickly point something out here, and that is that all you really have to show for this case is that Gn G inverse is contained in n. That's really all you need. And that's because, well, there was like a result when we did cosets that said something like all cosets are the same size. And so, I mean, this left-hand side is technically like a double coset. It's like a coset on the left by G and a coset on the right by G inverse. And then this thing on the right is also a double coset. It's just on by the identity on either side. And so all cosets are the same size. So if you have inclusion, then you have equality. So inclusion implies an equality. So you don't have to check it both ways. And I guess I should point out that the same thing goes here. So all you really need here is that Gn is a subset of Ng. For the same reason. Yeah, because like cosets are the same size or whatever. All right. And then let's maybe write down the element description of this thing right here. So this says for all little n in n, we have G little n G inverse is an element from n. So that's all we need for this case. That notice that's the same thing as saying that this is equal to like some n prime for the n prime and n, but we don't really need to go there. In this case, it's a little bit simpler to just write it down like that. Okay, so now here are some important things. So important is that, let's say this, if n is normal in G, then this object right here called G mod n, or the quotient group of G with n. So this is defined to be all the cosets. So Gn so that is a group. is a group itself. And so, you know, you guys watch some videos, some examples of this stuff. So it should be a little bit familiar. Is a group. And so if it's a group, well, you need to know what the operation is. And the operation is kind of exactly what you would like it to be. So let's say we've got two elements from this set of cosets G mod n. So one element would be like X n and the other element would be Y n. So if you combine them, you get X, Y, n. So that's the operation. Okay. And that's only if it's normal. If it's not normal, it's not a group. It's not like a well-defined operation or whatever. And then I guess I should say called the quotient group, but I won't write that down. And then number two, and this is like a really important, like quick result for checking that something is in fact a normal subgroup. So if the index of H in G is equal to 2, remember the index is the number of cosets, right? So the number of cosets of H and G is equal to 2, then H is normal in G. So I didn't use N there because sort of a priori we assume that N is normal just by notation. But here we're not assuming normality. We're just assuming this index is 2. That tells us that H is normal in G. And then we get some stuff for free out of this. So what kind of stuff do we get for free? Well, if H is normal in G, then that means that G mod H is a group, right? By this thing above. But it's a group with 2 elements, but there's only one like type of group with 2 elements, and that's Z2. So it's in fact just equal to Z2 or isomorphic to Z2. That's going to be always the case because there's only one group of 2 elements. Okay, then maybe one more. And this is another like also important way of testing if something is a normal subgroup, but not quite as quick as this one up here. And that goes like this. If H is a subgroup of G, is the only subgroup of a given order, and I should say finite, maybe this needs, everything needs to be finite here. It's the only subgroup of a given order, then H is a normal subgroup of G. So let's say you've got a group G and you make a picture of its subgroup. So we did that in the past. We made like a subgroup lattice, right? That was a picture of the subgroup, like a diagram of the subgroups. And you see that, oh, I've got this one subgroup and it's the only subgroup of the group that has 5 elements. Let's say all the other subgroups have a different number of elements that's not equal to 5. Well, that means that 5 element subgroup is normal. And so maybe Y. So Y. Well, that's because for all little g in G, GH little g inverse is also a subgroup of G. So this is called the conjugate subgroup. So I'll just say that in words, conjugate subgroup. So well, so that gives you another subgroup, but that subgroup has the same number of elements. So if it's got the same number of elements, but there's only one group with that many elements, then it has to be the group that you started with, right? So just to reiterate, let's say we know something about a group and we find a subgroup of G that has 5 elements, for instance. And it's the only subgroup with 5 elements. Well, we can make a bunch of more subgroups with 5 elements by doing this conjugation action. So for any G, GHG inverse is going to be another subgroup of 5 elements, but we know that there's only one subgroup of 5 elements. So that means all of those subgroups have to be the same. But if all of those are the same, then they're all equal to the original one H. But that means they satisfy this rule up here, right? But if they satisfy that rule up there, then they're normal. Great. This is really important, especially like, I mean, this is a fact that can be proven right now, but is especially important when you're like looking at the structure of sort of finite groups of small order and these things called CELO theorems, for what it's worth. Okay, so let's look at some examples from the homework. So let's look at this first problem. So there are 5. Oh no, I didn't mean to start you calendar. Get out of here, calendar. Okay, so there are 5 questions for this first problem. So what I want to do is look at each of maybe B and D. So they're all assigned, but I want to look at B and D, and then I'll leave A, C, and E for you guys to write on your own. So
What chapter again?
chapter 10. So this is 1B. So this says, this is essentially like we've got a group, we've got a subgroup. Check to see if that group is normal. Sorry, check to see if that subgroup is normal. If it's normal, write out the Cayley table for the quotient group or the factor group. So among A and D, exactly one of these is normal and one is not normal. So that's good. That'll give us a good sort of view into what can happen. Okay. So let's say we've got our group G, Star Trek Discovery t-shirt. Did you guys watch that show?
I'm not sorry right now. Star Wars is better.
Even though you hate all the new Star Wars.
Oh yeah. No doubt.
Typical internet person.
Only the first new one is good.
You're like plucked out of YouTube comments. I'm just kidding. I'm giving you a hard time. You can like what you want and don't like what you don't want. Okay, so we've got G is A5. And then we've got H is equal to the following 3 element group. So 1, 1, 2, 3, and 1, 3, 2. And I want to like point out that this is in fact a cyclic subgroup, and it's the cyclic subgroup generated by 1, 2, 3. I mean, how do we know that? Well, here's a fact. All groups with prime order are cyclic. You could prove that pretty easily just by taking a cyclic subgroup of a group with prime order, and the order has to divide the order of the group, but the order of the group's prime, so it has to be 1 over the prime. So anyway, now notice if you take 1, 2, 3 and you square it, you get 1, 3, 2, right? Because that you get that just from hopping 2 at a time. And if you cube it, you get the identity because it's a 3 cycle. So we know it cubes to the identity. Okay. Anyway, that was a long way of saying that we've got a cyclic subgroup 1, 2, 3. This is a subgroup of A5. Now, because I know something about the group AN in general and A5 in particular, I know that this is not normal. And that's because this A5 is something called a simple group, which is like a prime number. It's like the group form of a prime number. So it has no way of simplifying it. So it has no normal subgroups, but we don't know that yet. We haven't been proven that. So we would like to check that this is in fact not normal. So there's like a hint built into this. One hint is that it's 1B, so it's fairly quick. So sorry, it's fairly early in the homework exercises, so it should be fairly easy. And another hint built into this is that A5 has 5 factorial over 2, which is 120 over 2, which is 60 elements, right? But if it's got 60 elements, there's a lot to check, right? And since there's a lot to check, well, you would never be asked to check this much to find that it's actually normal. So you can deduce that it's not normal. Okay, so how can we find that it's not normal? So let's spell that out. Our goal is to find, I'll call it a sigma in A5, such that sigma 1, 2, 3, sigma inverse is not in H. Okay, so, well, I want to point out that we only need to worry about what's happening to this single element, 1, 2, 3, because it's the generator. In fact, whenever you check this type of stuff, you only have to check it with the generators. So if this is okay with the generator, then we're good to go. All right, so that will tell us. Anyway, that'll give it away. Okay. So we need to find a sigma in A5. Remember, those are all permutations that are even, right?
Right.
So I would say go for the lowest hanging fruit. So in your last homework it was the last homework. No, the last homework that was gradable. There's new homework due today, right? The homework that I gave back yesterday, you proved that every 3 cycle was even, right? Yeah. So that was in the last homework. Every 3 cycle was even. Well, that's probably the easiest example, is like take a 3 cycle. So let's take a 3 cycle, and it's got to be an A5, and it needs to be a bit different than this one right here. So maybe we'll take this. So let's try sigma equal to 3, 4, 5. So why 3, 4, 5? Well, it's got a little bit of overlap with 1, 2, 3, but not a ton, right? Okay, so if sigma is 3, 4, 5, then sigma inverse is equal to 3, 5, 4, right? We just write that in reverse. And now we look at sigma 1, 2, 3, sigma inverse. So that's going to be 3, 4, 5, 1, 2, 3, 3, 5, 4. So let's see, what is that? So let's see. Start with 1. So where is 1 sent under this map?
For 3.
No. So start here. 1 goes to itself with this part, right? 1 goes to 2 with this part, right? And then 2 goes to itself from this part. So if you start by plugging 1 into the function, you end up with 2 at the end, right? So 1 gets sent to 2. And then where does 2 get sent? So 2 gets sent to itself under this map, right? 2 gets sent to 3. 3 gets sent to 4. So in the end, 2 gets sent to 4. Well, look, we already see that we're in trouble, right? Because this doesn't look like anything from this set H, right? Yeah. But anyway, let's look at the next one. So let's do 4 goes to 5. 5 goes to itself. 5 goes back to 3. Okay. Now let's look. 3 goes to 5. 5 goes to it. Yeah. 3 goes to 5. 5 goes to itself. Wait, did I make a mistake? Four goes to. Oh yeah, I did make a mistake. 4 goes to 3. 3 goes to 1. Yeah, I did make a mistake. Sorry. So if we're at 4, 4 goes to 3. 3 goes back to 1. 1 goes to itself. So we close that off. And then I think you can check that 3 and 5 are both fixed. So 3 gets sent to 5 and 5 gets sent to 3. So 3 is fixed. 5 gets sent to 4 and 4 gets, so 3 and 5 are both fixed. Okay, so we get 1, 2, 4, but notice 1, 2, 4 is not an element from H, right? Yeah. So H is not normal in A5. Okay. Good. Let's look at D, and then I'll give you guys some minutes to work on A, C, and E. Okay. Okay, D is Q8. So G is equal to the quaternions. So let's recall that the quaternions are defined by plus minus 1, plus minus I, plus minus J, plus minus K. So there we've got an 8-element group, right? And then we have the following operation. So I squared equals J squared equals K squared equals -1. And then IJ equals K, whereas JI equals -K. Let's see. IK equals -J, KI equals J, JK equals I, KJ equals -I. And it might seem like that's coming out of nowhere, but it comes from the cross product. I think we described this earlier. But the motivation is that we've got this circle. And if you follow the arrows, you get the positive sign. And if you go against the arrows, you get a negative sign. So I times J is K. But J times I is -K because we're going against the arrows, right? Okay, then we're given a group, subgroup, I should say. And that subgroup is plus minus 1, plus minus I. And then I want to point out that this is also a cyclic subgroup. This is equal to the cyclic subgroup generated by I. We don't know that immediately because like groups of order 4 don't have to be cyclic, but this one is. Notice if we do, we'll do I squared is -1, I cubed is -I to the 4th is 1. So we get everything by looking at the cyclic subgroup. Now, let's look at the index. So notice the index of G and H, I guess I should say H and G. Well, let's use our notation here. This is the index of Q8 and the cyclic subgroup generated by I. So what's the index? Remember, the index is the number of cosets, but we also have a theorem, Lagrange's theorem, which tells us how to calculate that very, very quickly. What is it? What is it? So recall the general formula is if everything's finite, this is the number of elements in G divided by the number of elements in H. That's the index. So this is the number of elements in Q8 divided by the number of elements in this cyclic subgroup. So how many elements are in Q8? 8. Otherwise, why the heck are we calling it Q8, right? 8. How many elements are in the cyclic subgroup? Well, we already said 4, right?
Yeah.
1, 2, 3, 4. 8 divided by 4 is 2, right? Index 2 means normal, right? That should be like one of the first things that you think about when you're testing whether something's a normal subgroup or not. Okay, I want to find out if this is a normal subgroup. You should think to yourself, index 2 means normal. Can I use that? Index 2 means normal. In this case, we can. Over there, we couldn't, right? Notice the index over there is like 20 because it's 60 divided by 3. We didn't even worry about checking because that's very far from being index 2, right? But here we have this. Index 2 means normal. So yes, H is a normal subgroup of G. Or in other words, cyclic subgroup generated by I is a normal subgroup of Q8. Okay, so let's do the Cayley table. So this is actually really good because since it's index 2, there's only going to be 2 cosets. So we've got G mod H. Make sure I'm framed. Okay. So G mod H, which is Q8 mod cyclic subgroup generated by I, it's got to have 2 elements, right? The 2 elements are going to be cyclic subgroup generated by I and one other. One other because we know it's got 2 elements, right? There are 2 cosets. Then how do you find that other coset? Well, luckily it's easy to find the first non-identity coset because all you have to do is take some element not in the subgroup and do the coset with that coset representative. So let's take J I. So and then we're done because we know we have 2 cosets. Now, if we had 3 cosets or something, we would have to like look at the list of elements in each of those and pick something outside of that and then kind of repeat. So let's go ahead and just recall what we've got here. So I is equal to 1 I minus 1 minus I. So I've written it in order I to the 0, 1, 2, 3. And then let's look at the coset Ji. So that's going to be everything that's a left multiple of J, right? So if I multiply 1, I get J. If I do J times I get K. Wait, well, if I do J times I get negative K. All right, so that's J times I. Let's see, I'm doing J times I. And then I'll have negative J as the next one. And then positive K is the last one because I do J times negative I. So J times I is negative K, but then the minus signs cancel, right? So just to like be super thorough here, this thing right here is Ji. This thing right here is J minus I. Okay. So like, look, we got all the elements in the whole group out of those 2 cosets, right? Which is something that we should get because we know cosets partition the group. There we go. Okay, so now let's make a Cayley table. So we'll have our identity element, which is the subgroup itself, and then our non-identity element, which is the coset. Now let's make our calculation. So I'm going to put a phantom 1 here to just show that that is the coset of the identity. So remember, if you've got a normal subgroup, then the quotient group has the following operation: xn, yn is xy n. That's all we need to calculate. So let's see. 1 times 1 is 1, right? So we get that this is just 1n, right? And then 1 times j is just j, right? So that's just j, and then this cyclic subgroup. And then j times 1 is, again, just j. So this is j I. Now, j times j is -1, right? So this is the coset minus 1i. But from equality of coset theorem, we know that this is just equal to I. And that's because -1 is in the cyclic subgroup generated by I. Right? So recall that that's what it took for two cosets to be the same. There was like a big theorem about that. So there, we've got our Cayley table. If we put a 1 here, then we really have it, right? So now I want to point out that this is isomorphic to, so I'll write this out, G mod H is isomorphic to Z2, where we take 1i to 0 and ji to 1. Right? And over on this side, it's multiplication, and over on this side, it's addition mod 2. Yeah. Okay, cool. Okay, so let's look at this other, some of the other parts of this problem. Give you guys a few minutes to look at those, and then we'll sort of see how it's going. So this is a 10, exercise 1. So A, C, E.
Okay, let's go through A real quick because it's fast. And then point towards how to start B. Okay, so for A, it's S4 and A4. So normal or not normal? Normal, why?
Because it's, equals 2.
Yep, index 2 equals normal. That's right. So A4 and S4 equals 2. And that's because like the size of S4 divided by the size of A4 is 2 by, you know, a bunch of previous stuff we did, right? So that tells us A4 is normal in S4. That's all you have to check. It's great. Then next, make the Cayley table. So we can make a quick list of all of the cosets. So S4 mod A4. So that's the quotient group or the set of subsets. It's the same thing at this point. So we know that we should have the subgroup itself. And then we pick one element. We pick one element. We pick one element not in the subgroup. And we might as well pick 1, 2. So that's not in the subgroup. We know because it's, how do we know it's not in the subgroup? Because it's a single transposition, which means it's written as an odd number of transpositions, that odd number being 1, but 1 is odd, right? Yeah, so that means 1, 2 is not in A4. So that's a complete list of cosets. Now we can make our Cayley table. So we've got A4. We've got 1, 2, A4. We've got A4. And we have 1, 2, A4. Like that. And then, well, this is going to be just A4. This one's going to be 1, 2, A4. Here we have 1, 2, A4. Remember, there's an understood identity right here. So I'll put it in orange. There's an understood identity right there. So when we do the combination there, we're really doing identity times 1, 2, but you know, identity times anything is identity. And then 1, 2 times 1, 2 is the identity, right? Because it's a transposition squared. So that gives us just A4. And then again, we've got like an understood identity there, which I'll put in orange. So there's our Cayley table for the quotient group. So notice it's Z2 again, right? Well, also all groups of order 2 are Z2, so good. Now let's look at let's maybe look at 2. So maybe give 2 a start, and then we'll look at it. Just a little bit more to do for 2.
so.
Go from the upstairs. Like I was saying, 10 volts yesterday. Yeah, cause actually, you're not there, so I have to move some crap, and then, I have to like build the shelf later. And whoever had the scene shot before Heather didn't label things properly. And I had to figure out which dead ones worked and which ones didn't inside, we grabbed like a knife, and I keep going like this, there was like 142 screws. That I had to test, and some of them need to differ on the way. Now this needs to get recounted.
I gotta figure out what classes to take. I know I gotta take math, but and another group over in
We definitely gotta figure that out. It might as well be a stop this year because of the whole take two thing.
All right, let's look at this one. Where'd you go? Okay, find all the subgroups of D4. Which subgroups are normal? What are all the factor groups of D4 up to isomorphism? All right. So D4, so the dihedral group of order 8, right? So the dihedral group of the square. So, you know, it's made up of 4 rotations and 4 reflections. So it's useful to like kind of write down all those rotations and reflections real quick. So D4, so this looks like E, R, R squared, R cubed, and then S, SR, SR squared, SR cubed, right? So we've got rotations, reflections. Then we know D4 has 8 elements, right? So that means we have the following possible orders of subgroups. 1, so that's kind of boring, right? That's just the identity. 2, 4, 8. 8 is also kind of boring. That's the whole group, right? And why is that? By Lagrange's theorem, the order of a subgroup has to divide the order of a group. So it has to be those types. Okay, let's make a picture of the subgroups. I think we've made this picture before, but you know, it's useful to see again. We've got D4 there. Now we want to look for 4 element subgroups first. Maybe actually before we get started, let's go ahead and write down just the singleton subgroup down here, which is the identity subgroup. Now, we want to look for 4 element subgroups first, so maybe working down. So notice that there's a very obvious 4 element subgroup, and that's just the rotations, right? So that would be the cyclic subgroup generated by R, but that's equal to E, R, R squared, R cubed. So there. So that would be one subgroup of order 4. Then there's actually one more subgroup of order 4. And that is like essentially D2, which is the subgroup of a rectangle. So a square is a type of rectangle, right? And so the symmetries of a rectangle should be a subgroup of the symmetries of a square because the square is a type of rectangle. Squares allow for 90-degree rotations, whereas rectangles only allow for 180-degree rotations, right? So that's given by R squared and S. So R is the 90-degree rotation. R squared is the 180-degree rotation. So again, that's 4 elements. E, R squared, S, SR squared. That's actually an abelian group. You can prove that all elements or all groups of order 4 are abelian groups. Okay, now we need some groups of order 2. So let's build it up from here. So we've got one group of order 2, which is just rotations. So that would be the cyclic subgroup generated by R squared. So that's like the identity rotation and then 180-degree rotation. That's it. Okay. And then notice that that is inside of the group of all rotations, right? Yeah. It's also inside of that, right? That also has a reflection. And then we've got one more subgroup of order 2, and it is the subgroup of, actually, no, we've got a couple more. We've got a couple more subgroups of order 2, and they're related to reflections. So we've got the one generated by S. So that's going to be E and S. So that's reflection about, one of our given axes. And then we've also got the subgroup generated by SR, the subgroup generated by SR squared, and then the subgroup generated by SR cubed. Those are all subgroups of order 2 because all reflections have order 2, right? Yeah. If you put 2 mirrors back to back, you get the same picture, right? It's a reflection. Okay, so anyway, we've got 1, 2, 3, 4, 5, 6, 7 interesting subgroups, right? Now, which ones do we know are normal immediately?
Whatever has a two, then.
Yeah, whatever has an index of 2. So which ones have an index of 2?
R squared.
No, that has an index of 4. Yeah. So index is not the number of elements. Index is the size of the group divided by the number of elements.
So what about R squared?
So D4 has 8 elements, right?
Yeah.
So for the index to be 2, then we need to look for subgroups of order 4. Right? Because 8 divided by 4 is 2. So yeah.
That one right there.
This one is normal. This one is normal immediately.
Yeah.
There's like no work that you have to do to show that those are normal. And then it says to like say, well, what groups are they isomorphic to? That's another question. Like what familiar group is the quotient group isomorphic to? Well, again, there's nothing to do there because there's only one group of order 2, right? So we know the quotient group is going to be of order 2 because it's of order 8 divided by 4, which is 2. But there's only one group of order 2, which is Z2. Same thing here. So D4 mod R squared S is also going to be Z2. There's nothing to do there either. Okay, so now let's look at one of these others. So we've got, if I remember correctly, we've got one more normal subgroup. I think this one is normal, but these 3 are not normal. So let's just do that as a claim, although you might want to do some exploration to come up to this claim. That is the cyclic subgroup generated by R squared is normal in D4. Okay, so here's like a fact. D4 is generated by R and S, right? And then R squared is going to be the same thing as R squared R. That's like pretty clear. Just you can write out the elements. So notice the elements here are going to be R cubed. The elements here are going to be R cubed. So as cosets, those are the same, right? So that means we're only left to check one thing. So need to check SR squared equals R squared S. That would be the last thing that we get to check. And why do we only have to check those 2 elements? Because those 2 elements are the generators of D4. So if you want to check something about the properties of a group, you only have to check it about the generators. So D4 is generated by that single reflection and that single rotation. So any property you check about this subgroup, you only have to check about the generators. So let's do that. So let's do S R squared. Sorry, are we okay?
Yeah, you're fine. We gotta do the extinguisher, sorry.
All right. So SR squared, so that's going to be S. And then let's write this as ER squared. So that's going to be SSR squared. And then the standard is to write this with the S's to the left, right? That's the standard way to write an element of the dihedral group, so we can stop. Now let's look at R squared S. So that's going to be ER squared times S. So that's going to be S R squared S. But now this guy right here is equal to SR to the 4 minus 2. And that's because in dn, R to the KS is equal to S R to the n minus k. Oh, that was like derived inductively in some video or something. So we can commute any power of R past S, and we do it like this. We do the total number of the group, so this is D4 in this case, minus our power. But notice like 4 minus 2 is 2, right? So that means these two are the same. So we got it, right? So now this is normal. So that finishes that this is normal. Okay. So now we can look at all the cosets. So D4 mod R squared. So that's going to have 4 cosets. We know it's going to have 4 cosets because R squared has 2 elements, right? D4 has 8 elements. 8 divided by 2 is 4. So this should have 4 elements. This quotient group should have 4 elements. So it's got the identity. So I'll write it like this. You can leave off the E if you want to, but I'll write it there just for thoroughness. And then we've got R times R squared. We got that one, right? So that was this coset up here, right? Yeah. And then we've got this one right here, which is S R squared, right? And then we're in luck. We know that this is a group. So that means it's closed under the operation. That means that SR R squared has to be our last element. And now you can make a Cayley table to figure out which one it is. So I'll let you guys look at what the Cayley table is, but notice that if you multiply this by itself, you get R squared coset with R squared, right? But then you can bring the R squared in. So that's just the identity, right? So this squares to the identity. S also squares to the identity because you get S squared, which is the identity, right? And then this SR is a reflection, so it squares to the identity. So all of these things have square to the identity, but the fact that they all square to the identity tells you that your isomorphism is with Z2 cross Z2. As I think we discussed last time, that whenever you have a 4-element group where everything has order 2, it's got to be Z2 cross Z2. Or, this is also D2. Sometimes it's called V4, the Klein 4 group. They're all the same. Okay, and then, so that's kind of left to check just by making a Cayley table or something. And then also left to check is that these guys are not normal. that finishes off that one. So I think I really like this problem because we get these two things for free, right? Because of the index, but then we have to do a little bit of work for the rest of it. Okay, does that seem okay?
Yeah.
Okay. So I think we're good. Are we good? Okay. I'll see you guys in a bit.
Yeah. Hour or so.
Solid.
Did you like this week's episode of Falcon and Winter Soldier?
I did.
Yeah, that part was crazy.
Did you hear about this theory that one of the overarching plots of the season had to be changed at the last minute because it was about a pandemic?
Yeah.
Was
Yeah.
a little too topical.
Yeah.
Yeah. I obviously saw that too, because I brought it up. Yeah, I'm liking it.
Good great episode though.
I think there's 6.
Thanks.
Yeah.
That's gonna be low, dang, whatever that's coming out.
I'm real